Some judge. Go, no, go.
Next year when I file my taxes, I'm going to include the cost of this paper and the ink and print. It might actually make a difference.
Are the lights different today?
They're brighter.
I feel like they're more bright.
It's like there's one light, the brightest spot is right in front of the screen.
Maybe you have one out and the janitor finally did his job.
Does that help?
Yeah, it's perfect.
That one?
I'm probably not gonna be able to see it.
Not gonna fall asleep?
Sleep sounds good.
Yes to you're not gonna fall asleep, or yes you're gonna fall asleep?
Gosh,
So today we're going to start talking about solutions. So we're moving on from gases. We're going to talk about solutions. When you think of a solution, what's the first thing that comes to mind? Math. Complicated. Liquid? Okay. So we'll see that solutions don't have to be liquid, but by far most solutions we deal with are liquid, which is why liquids popped into your head. Okay. And we're also going to find out what a molar solution is. So last week in lab, you used 0.1 mHCl, and you probably had no idea what the heck 0.1 mHCl was, right? You didn't need to know, right? But now you need to know, so now we're going to go over it. So there are three types of mixtures, okay? There are suspensions, colloidal suspensions, and solutions. Looking at these, the answers are right there.
Would have been nice if you just went with that. It looks smart.
So this one's a suspension, it's a colloid, that's a solution. How can you tell them apart by looking at them? What's different? How clear they are, right? A solution, I could tell you that was pure water, not a solution, and you would have no basis of arguing with me, right? It looks just like water. Suspension, if you got right up here close, you could probably see that there are actually little pieces of stuff floating around in there. A colloid looks like water, but it's just a little cloudy. You can't really see any individual particles, but it's a little cloudy. Okay. And so really the only difference is the size of the particles. In a suspension, they're big. In a solution, they are at the molecule atom ion size. It's one single thing. It's not a group of things. And a colloid is somewhere in the middle. Okay? A suspension will settle out. I get in trouble. Telemarketers are calling me all day.
Getting the 615 number, I've been getting one of them.
No, it's 352. It better not be Geico.
One of us has one.
Rude.
That's just Daniel's song.
So a suspension will settle out. A solution definitely will not. Okay? A colloid, unless you do something to it to make it settle out, like put it in a centrifuge or something, it won't settle out. A suspension, if you just set it on a bench, it'll settle. A solution, doesn't matter what you do to it, it is not going to settle. A colloid, you need to put it in a centrifuge or something, make it settle. Okay. Colloids are not common. Solutions are really common. What's an example of a solution? Water and vinegar. Salt water. What do you think is an example of a suspension?
Jello, golf, beer.
Fragile suspension.
Beer doesn't sound very good.
Actually, beer, who said beer is a solution? Because nothing's going to settle out of beer. Unless it's not.
How hoppy it is.
Does stuff settle, I'm not, I don't, can't stand the taste of beer. Does stuff settle out of beer? Okay. I suppose if you have beer that something's going to settle out of it, it would be a suspension.
Solution's gonna make sense in a little bit with the beer.
Okay.
Gas is
The
sleeping.
Jello, that's not a suspension. Nothing's going to settle out of Jello. What's the third thing I heard? I heard
Cough syrup.
cough syrup. Nothing's going to settle out of cough syrup. What's something that if I had in a glass lemonade with pulp in it, not country time, right? Real lemonade. Country time would be a solution. But if you had real lemonade with pulp in it, the pulp's going to suck. What else? Oversaturation. So if you put, say you're making salt water and you put too much salt in there, it didn't completely dissolve. If you stop stirring, the rest of it's going to settle out. That's a suspension with a solution. What else?
The flagell, we crush a tab, a solid tab, and you put it into some sort of water base, so it's a suspension because you've got little particles and solids moving around in it
Okay.
to deliver it.
What else?
I was thinking like water.
Lake water? Yeah. Very good. Yeah. So water out of a lake, out of a river, out of the ocean, there's probably particles in there that if you let it sit there, it's just going to sediment out, right? But tap water, in this, unless you really want to get technical, is not a solute, is not a suspension because there really isn't stuff in there unless maybe you have a really bad well or something. Okay. Solutions are really important in medicine. Okay, there are lots of different types of solutions. The biggest one are water solutions, definitely, because we are one big water solution basically. We have salt, we have proteins, we have nucleic acids. All that stuff is dissolved in water in us. We're one big walking bag of solution. Okay. You can also have a gas solution. So if you have air, air is made up of mostly of what?
Nitrogen.
Nitrogen. You can describe air as a solution of gases in nitrogen gas. Okay? So if you're giving someone air, or probably oxygen, does anyone use oxygen to give patients? Is it pure oxygen or is it mixed? It's probably mixed,
It
right?
should be pure oxygen with some kind of a...
So here there's nitrogen and CO2. Okay. But the ratio of oxygen, nitrogen, CO2 in here is different than what's in the normal air. If you put pins into someone who had a very, very painful accident, it's like, this is a titanium pin with a little bit of aluminum and vanadium in it. So that's a solid, it's actually a solid solution. Okay? We definitely don't normally think of solutions being solid, but that is a solid solution. There are multiple parts of solutions, and in problems and things, we're going to refer to them by their name. So it's important to get these straight. The solution is a homogeneous mixture. Remember we talked about heterogeneous and homogeneous mixtures. A solution is homogeneous. If you have salt water, just pure salt water, there's the same amount of salt in the water at the top as there is at the bottom. It's homogeneous. The solute is the thing that's being dissolved. Generally, that is present in a smaller amount. Okay? You could make a case that if you put a little bit of water and a whole bunch of salt, that the water is dissolving in the salt. Okay? For the most part, you will be safe saying the thing that's the less of is the solute. That's the thing that's being dissolved. So if I have a glass of water and I pour a teaspoon of salt into that, what is the solute? The salt. Okay. So going back here, what is the solute in this liquid solution? Sodium chloride. Okay. You could say sodium ions and chloride ions. It doesn't matter. This one's a little tricky because there's kind of equal amounts of a lot of things. We won't touch that. This one, what are the solutes in the solid solution here? Aluminum and vanadium. There's a whole bunch of titanium, a little bit of aluminum, and vanadium. Yeah.
So would that mean alloy solution?
In a sense, yes. So if the solute is the thing that there's less of, the solvent is the thing that there's more of. Okay. This one is probably a little easier to remember because you think of solvents. Solvents dissolve things. You use it in hardware stuff, just around the house, handyman type stuff, right? Solvent is the thing that's doing the dissolving. There's the most of it. So if I have my glass and I put a teaspoon of salt in it, what's my solvent? Water. Okay. Generally, around the house, at work, things like that, you talk about solvents, you're generally talking about organic, really strong, dangerous chemicals. But to us, a solvent is anything that can dissolve something else. Water is a solvent, okay? And nitrogen gas in the air is a solvent. Solid titanium in that pin is a solvent. And then the last thing is aqueous solution. We've already talked about aqueous solutions. An aqueous solution is just a solution where there's a solute dissolved in water. That just means that the solvent is water. In this situation, we don't know what that is. We don't know what this is. But we can tell which is the solute.
The white crystal.
The white crystals, right? There's clearly more of the liquid than the solid. So that means what is the solvent?
Clear.
The clear liquid.
colorless liquid.
That's probably salt dissolving in water. We can talk about solubility, and you've probably seen this word places before. What it really means is how easily something dissolves in something else. Okay. How readily or completely a solute dissolves in the solvent. And remember, when ionic compounds dissolve, they break apart. Ionic compounds break apart, molecular compounds do not. So if you put a soluble ionic compound into a solvent that it's soluble in, like water, it's going to break up into its ions. If you have an insoluble compound, whether that be an insoluble ionic compound, an insoluble molecular compound, it basically just stays as it is. It just kind of sits there. It doesn't do anything. We've already used the solubility table, right? And if you looked at that, there are some patterns, but it's pretty much unpredictable. Okay? So, everyone feel confident using this? Remember, this is, in one form or another, is on the cheat sheet. You don't have to memorize it, you just have to be comfortable using it. We can do things to change how fast something dissolves. What can we do to make something dissolve faster?
Heat it.
Heat it. What else? Shake it. Anything else? There's 3 of them. That's a little too complicated. Is it on the slide?
Yeah. Says the surface area.
I'm just not saying it because
Increase surface area.
Yeah.
Thank you. Okay. So the temperature. You're making Jell-O. Anyone tried to make Jell-O with cold water? It does not work, right? You have to heat it to get the gelatin to dissolve, and then when you put it in the fridge, it cools off and comes back out of solution, okay? You can change surface area. If we put a sugar cube into water, and we put normal granulated sugar into water, which one's going to dissolve faster? The granulated. That's because for something to dissolve, it has to be touching the water. If I put this sugar cube in the water, the stuff in the middle of the cube isn't even touching the water. So the only stuff that can dissolve is the stuff on the outside. That dissolves, and the next layer dissolves, and the next layer dissolves. But if I put this in the water, almost all of it is touching the water, and it can dissolve a whole lot faster. You can also mix things to make them dissolve faster. So when you make Kool-Aid, if you just took water and poured the Kool-Aid in, put it in the fridge, you're going to be very disappointed when you come back later, right? Yes, it's cold. You don't have to heat it because it's just sugar. But you have to mix it. Otherwise, it's going to sit on the bottom of your whatever you made it in, and it's not going to dissolve. When you pour it off, it's just going to taste horrible. It's going to be food coloring in water, probably, right? So you have to mix it in order to make it dissolve faster. Sports drinks like to talk about electrolytes, okay? And if you've noticed lately, the commercials for Gatorade and Powerade and things like that, at the end, they say electrolytes for taste only. Now, I'm guessing somebody got sued, okay? An electrolyte is just something that when it's dissolved, has a charge. Any ionic compound that dissolves in water will make ions. So the ions have charge, it's an electrolyte. An electrolyte, by definition, is something that, when dissolved in water, will conduct electricity. We talked about, probably a month or more ago, for something to conduct electricity, you have to have charges. In a solution, those charges are in the form of ions. So if you have an ionic compound that dissolves in water, it will break apart into ions, conduct electricity, and that makes it an electrolyte. There are strong electrolytes and weak electrolytes. The difference is how much they dissolve. If I put sodium chloride in water, assuming I don't go above the solubility limit, which we'll talk about, it's all going to dissolve. That's a strong electrolyte. It dissociates completely. A weak electrolyte only partially dissociates. That could be an ionic compound that's only a little soluble in water, or I think what we'll use in lab is vinegar, acetic acid. Acetic acid is not an ionic compound. It's actually a molecular compound that will dissociate a little bit. And we're not going to talk about why or how, but all you need to know is it'll dissociate a little bit. And so acetic acid is a weak electrolyte. If you have sodium chloride solution and acetic acid solution that are the same concentration, sodium chloride solution will conduct electricity a whole lot better than the acetic acid. And then something that either does not dissolve, like silver pretty much anything, silver chloride. Silver chloride is not soluble in water. It's an ionic compound, but it's not soluble, so it's a non-electrolyte. Okay? Methanol, ethanol, things like that. Those are molecular compounds. They're soluble in water, but they don't dissociate at all. So you don't get ions, No charges, no electricity. Those are non-electrolytes. What we're going to do in lab, possibly this week, is test things to see how good of an electrolyte they are. What you're going to do is you're going to have a little light with two little wires sticking down. You just stick it in a solution. If the light comes on, it's an electrolyte. Okay? So that's all this is here. This is a light bulb hooked up to electricity. Electricity comes in here, comes down here, but then to complete the circuit, it has to go through the solution over to here, back up into the light bulb. So if this is just plain water, pure water does not conduct electricity. But if we put HCl, sodium chloride, NaOH, and nitric acid, those are all strong electrolytes. They dissolve, they make ions, they create charges. Now all of a sudden our water will conduct electricity. Oh, I deleted that. You know this. We've talked about it many times. Sodium chloride associates in sodium chloride. HCl. I swear I deleted these. The gremlin. HCl breaks apart into hydrogen ion, and chloride ion. NaOH breaks up into sodium and hydroxide ions. This is hydrogen peroxide. Hydrogen peroxide does not break apart. Hydrogen peroxide liquid just goes to hydrogen peroxide aqueous. Okay? That means we took it out of the bottle, assuming that was pure hydrogen peroxide, which it's not. And we poured it into water. It did not break apart, but it is dissolved in the water. So it's an aqueous solution, but it's a non-electrolyte. So, if I were to put zinc chloride solid in water, what would I get out of that? What would it dissociate into? Yes. Zinc chloride solid goes to, you're going to break it apart, you have a zinc. What's the charge on this zinc? 2 plus. Plus chloride ion with a -1 charge. Is it balanced? No. There's 2 chlorines here, you have to have 2 here. Now these are aqueous. What about KNO3? What do I get when I put that in water? I'll tell you, it is soluble.
Potassium ion and the ion.
Yes. We have potassium ion and the nitrate ion. And they are aqueous. That last one is ethanol. You put ethanol, liquid ethanol, in water, what do you get?
Liquid ethanol diluted.
What do we write it as? How do we write that out? C3H5OH liquid goes to C2H5OH what? Aqueous. So the ethanol itself did not change whatsoever, but it went from being a pure liquid into an aqueous solution. There are 3 things that alter how much of something you can dissolve in a solvent. First, structure, meaning what is the compound you're trying to dissolve. Another is temperature. Just like increasing the rate of dissolving, increasing temperature generally makes things more soluble. And if you're dealing with solutes that are gases, pressure will change the solubility of that gas in the salt. So with structure, this comes back to that like dissolves like. If you look at that giant molecule, you have a whole bunch of carbons, a whole bunch of hydrogens, right? What's special about bonds between carbons and hydrogens? They're non-polar. Carbon-hydrogen bonds are the only bonds between two different elements that are still considered non-polar. So we have this giant molecule. The only thing that is not non-polar bond is the CO and OH bond. That makes up a tiny little portion of this gigantic vitamin A molecule. Okay? So this is not very polar. As a whole, you would call this non-polar. This is vitamin C. There's a lot more oxygens, and as a whole, the whole thing's a lot smaller. So this is a lot more soluble in water. Have you heard of water-soluble and lipid-soluble vitamins? Which one do you think is which?
A is lipids, which is hydrophobic,
Right.
and C is hydrophilic.
Like dissolves like. Lipid-soluble vitamin is going to be non-polar because lipids are non-polar. Which question?
Did you delete a lot of slides?
No, they're hidden, they're, like, you have to, it jumped. So, like, you had to, like, go, it's a big jump.
Well, like 6 pages.
I will-
9 slides.
I'll bet you what happened is I probably didn't upload my version of the ones with the cutout slides. The ones where I said I thought I cut those out, did you have those?
Yeah.
Yeah.
I don't know.
How many slides do you have in total?
I think there's 66?
Yeah, we have 90.
Okay.
I wasted a lot of your tax dollars printing this.
So someone will email me to remind me, I will cut out what you don't need to know and repost it. Okay. So this is nonpolar. It will dissolve in nonpolar things. Lipids, fats, are nonpolar, lipid soluble. Vitamin C is polar. Water is polar. Vitamin C is a water soluble vitamin. That is a fat molecule. Okay? There's 3 giant chains here that are completely nonpolar, and then there is a little bit on the end here that is polar. Overall, would you say this is polar or nonpolar? Nonpolar. And not just because it's the title of the slide. There's a whole lot more of the nonpolar than there is the polar. Okay? Anyone know what a detergent, it's like a soap molecule looks like? It's basically one of these long chains, but this head on the end here is very polar. So what you have is one molecule that is very nonpolar on one end, very polar on the other, which is why soap will let fat dissolve in water. It basically acts as a translator between the two. It keeps them from coming into contact with each other. Both the water and the fat can be dissolved by the soap molecule, and so in effect, the fat becomes soluble in the water. Why do oil floating on top of the water here and water not mix? Right. Oil is very nonpolar. So water is polar, oil and water don't mix. CCl4. C6H14 are both non-polar. If you put CCl4, carbon tetrachloride, in water, it would not dissolve. If I put hexane, C6H14, in water, it will not dissolve. But if I mix the two together, they do dissolve with each other. Why?
Choose polarity going on.
They're both non-polar. Like dissolves like. If they're both non-polar, they'll dissolve in each other.
So if anything is, if it's a mixture, if they're all like polar, then that whole thing is polar. Or if they're all non-polar, then the whole thing is not polar.
You wouldn't say this as a whole is polar or non-polar. It's a solution made up of polar things.
Okay.
Or it's a solution made up of non-polar things. What do oil and vinegar not mix? Right. So oil is fat, so that's non-polar. If they don't mix, by process of elimination, you can figure out that vinegar must be polar. But Ben was actually able to look at the picture and see it's small. There's a lot of different colors here. It's probably polar. And vinegar is polar. This is just, again, like dissolves like. We have an ionic or a polar molecular compound. It's soluble in a polar solvent, insoluble in non-polar solvent. A non-polar solute is only soluble in a non-polar solvent. Which of these three types of solutes would be soluble in water? Ionic, polar, non-polar. Which ones are soluble in water? Ionic, is that the only one? And also polar. Water is a polar solvent, so it's ionic and polar. What about methanol or iodine? Which one would be soluble in water? Methanol. Methanol is polar. I2 is completely non-polar. Which one would be more soluble in benzene? Benzene is C6H6. Iodine. Benzene is non-polar. Iodine is non-polar. Iodine is more soluble in benzene. Temperature affects solubility. If you, like with the jello, which we talked about the jello, if you heat it up, it dissolves, and you put it in the refrigerator, and it comes back out of the solution. Okay. Temperature will affect the solubility of most things. We're not going to have any, I don't believe, any examples where temperature does not affect the solubility. Most ionic solids are more soluble in warm water than cold water. And that makes sense to you. So don't make it that harder than it has to be. Something is more soluble in warm water than cold water. Where it gets tricky is gases are actually less soluble in warm water than cold water. It's reversed. Okay? Come up with a way to remember that. Okay? The way I remember it is I fish bass tournaments. Okay? In the summer, I put a fish in the live well in the boat. It's really hot. There's not much oxygen dissolved in that water. We put ice in the water to cool the water down so that more oxygen will dissolve in the water. Okay? That is literally how I remember that gases are less soluble in hot water. Okay? Come up with your own way. At the molecular level, basically what's happening is if you have a beaker and you have the water in there, and you have some gas molecules floating around, when you heat something, it wants to turn from a liquid to a gas, right? The more you heat something, the more it wants to be a gas. So if this is hot, these gas molecules want to be gas molecules floating around up here. Okay. So whatever makes sense to you, remember, solids are more soluble in warm water. Gases are less soluble in warm water. This is a solubility curve. Okay. So we have temperature on our x-axis going up. This is the solubility of different gases in water. Here's oxygen, nitrogen, and argon. Okay? All of them decrease as temperature goes up, but they decrease different amounts. Argon is very low solubility to begin with, but it does actually go down. Oxygen is very soluble in water, and it decreases very fast. The way you read this is if you want to find out what the solubility of a gas is at a given temperature, say room temperature 25, just go to 25, go up till you meet that line, go over, that is about 0.00025 grams of argon gas in 100 grams of water. Okay. You won't really have to read any of these. Okay. But that is what this means. The y-axis is how many grams of the thing you can dissolve in 100 grams of water. So if something is high solubility, you can dissolve more of it in the same amount of water. Does that make sense? So I would say salt has a very high solubility in water. That means you can dissolve more of it in the water. And if you were to heat the water with a solid, what would you expect these curves to look like? The opposite. Right. So if I have this with temperature going that way, increasing solubility going up, at very, very cold temperatures, they're not really soluble. So they start here, and they're going to go up like that. Okay. Eventually, you're going to reach a point where it doesn't matter how high you heat it, you're not going to get any more in the solution. We can also change the gas pressure to alter the solubility. And this actually is very relevant to you. It's something you deal with a lot. You just don't know it. Okay? Gas pressure will affect the solubility of gases, but not liquids or solids. The higher the pressure of the gas above the liquid, the higher the solubility in the gas. So if I have a closed container this time, and I have my water here, and I have, say, oxygen gas up here, and I have a matching container, and there is less oxygen gas up top. Which one has the higher pressure of gas?
One to
The
right.
one on the right. Why?
More molecules and same size things.
Right. That's the relationship between number of moles and pressure. Increase the amount of a gas, the pressure goes up. Right? So which one has the higher solubility of the gas in the water at the bottom? The one on the right. The higher the pressure, the higher the solubility. Think of it, if you have a high pressure, it's going to push that gas down into the liquid. That's how I remember that. Okay? If you have more of it up here, you're going to have more of it down there. It's just logic. So, I don't remember if there's another bullet. Is there another bullet point here?
It says an increase in pressure results in an
Okay.
increase in cycle.
Yeah. So you increase the pressure, you increase the solubility. Can anyone think of, I said this is incredibly common in your life. Where?
Sodas, beer.
Soda. That is why when you take that cap off, the bubbles come out. When they seal that bottle, they have very high pressure. And so there's high pressure in that little space of gas at the top of the bottle is very high pressure, which makes a lot of that gas, the CO2 carbonation, go into the soda. You crack that lid, all of a sudden this pressure equalizes with the atmosphere, and all of a sudden you have low pressure, low solubility, and the bubbles form. When you put the cap back on, the bubbles will come up, increase the pressure up here again, to the point that you reach an equilibrium, and the bubbles stop forming until the next time you take it out. Until the next time you take the cap off, eventually all the CO2 dissolved in your soda will come out, and then you have a flat soda. So we can change this if we have a little cylinder. So if we have a liquid here, our gas here, we have a piston that we can move up and down. We can actually make gas go in and out of solution at will. So if I take this piston and I push it down, I'm going to increase the pressure, basically pushing the gas here into the water. If I pull it back up, you're going to more or less create a vacuum, pulling the gas out of the water into the upper part. So that's what we talked about. Loper knows this one. When a scuba diver goes to really deep in the ocean, there's very, 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 very high pressure down there. What happens to the solubility of the gas that they're breathing in their blood? It goes up. But what happens when you come back up to the surface? Your solubility drops.
Comes out of solution into.
So you have a soda bottle in you. You are one big soda bottle at that point, and the bubbles form in you. And that's not good, right? So if this cap at a very high pressure at the bottom of the ocean all of a sudden comes up to the surface, the cat's going to get what's called the bends. Okay? Basically, bubbles form in your body. If you want to cure the bends, how can you do that?
Pressurized and
Hyperbaric chamber. You put them back into a pressurized system. The solubility of the gas, the bubbles in their body will redissolve in their blood, and then you can slowly bring them back up to atmospheric pressure. Which is why if you scuba dive, when you come back up from deep, you're supposed to go very, very slow. The only time you don't is one, say you run out of air, you can't breathe anymore. I would rather deal with the bends than a lack of oxygen, right? Yes?
that probably won't be the same thing as the bends. Your gas will be expanding inside your lungs too.
Right.
Pneumothorax instead of the bends, and it's much more difficult to treat that than it is the bends. So you want to tilt your head back, come up slowly anyway, and let the gas escape as you're coming in.
So you're saying even if you run out of gas, if you were down 30 feet and you ran out of air, you would come up slowly.
Absolutely.
You're well trained. I would not. I would get up as fast as I possibly could.
There's another part, yeah, that would be really more dangerous, but the other part to it is, you're not supposed to be alone, there should be somebody there with you. And you should have staged decompression stops on your way up, and there should be a go-home bottle in for those stops. Should. It's not practiced very often, but
Let's say your buddy gets attacked by a shark at the same time that you run out of air. he needs to get to the surface really fast.
That's
And
great.
so do you.
Scream as you're going. It'll scare the shark.
Okay.
That's the difference between open water diving and cave diving.
Oh, cave diving.
Open water,
Crazy.
man, that's, no.
Yeah.
Yeah, cave
Cave dive,
diving.
you're not gonna get the bends cave diving, that's for sure.
No, you get lost and disoriented. Your
Right.
up and down are not relevant
Okay.
anymore.
So, now that we know what a solution is, we can talk about numbers of concentrations. Okay? We can measure the concentration of solution a number of ways. Basically what the concentration tells us is how much of the solute there is versus the solvent. Normally, it's the solute that we want. Okay? When you have those dropper bottles in lab, the sodium chloride solution, the 0.1 m HCl, the potassium nitrate, all those things, the reaction has nothing to do with the water, right? It's what's dissolved in the water. But if you just took some solid HCl and mixed it with a solid something else, they're just going to sit there. They need to be in the ionic form to react. So we need to know the concentrations of the solutes in the water so that we know how much of what we actually care about we're using. A saturated solution means that you cannot dissolve any more solute in the solvent. That means you are right on that solubility curve. If you add any more, it's not going to dissolve. An unsaturated solution means you're below that curve. That means you can add more and it will dissolve. In certain situations, what that's telling us is how many grams of our solute, how many grams of our sodium chloride we can dissolve in 100, say 100 grams of water. Okay? A supersaturated solution is a special situation where you actually have more dissolved in the solution than that graph says you can. Okay? And you have to do things in a specific order to do some little magic to get to that point. Okay? Has anyone ever made rock candy? How did you do it?
Heated up the sugar and water and put a string over
Right.
a glass of water.
So when you heated the sugar in the water, what happened to the solubility of the sugar in the water? It went up, and then after you heated it and you put the string in it, what did you do to it? You let it cool. When it cooled, what happened to the solubility of the sugar in the water? It went back down. So then what happened to the sugar? It came out of solution. For a split second, you had a supersaturated solution. Okay? The temperature dropped, the solubility dropped, and then the sugar came out of solution. Okay? If you had a container, you dissolved that sugar in a container, there was no string, and that container was completely smooth on the inside. And you lowered the temperature very slowly, what you would find is that you could get back to room temperature and the sugar wouldn't come out of solution. But according to that graph, that's impossible. What happened was for a crystal to form, it has to have something called a nucleation site. A crystal has to form on another crystal. If there's nothing in there for it to form, it can't form a crystal. Even if it wants to, it can't. Okay? So, this is a supersaturated solution. There's more of a solute dissolved in this liquid than should be. If we drop in something called a seed crystal, all of a sudden we get crystals forming, and then before you know it, we have a whole bunch of crystals. And that's now come back to be a saturated solution. And this is all the extra that was dissolved here that shouldn't have been. Yeah.
Let's suppose this also works with certain things with boiling point. Like heat them up.
Oh,
at boiling point,
yeah, so
and
it-
boil.
Yeah, so it's not a supersaturated solution, but it's the same idea. Mythbusters actually did this. The idea is if you put a bowl or a cup of water in the microwave and heat it up to boiling, if your mug is completely smooth and there's nothing in there, you'll get above the boiling point of water, but it won't boil. You then take it out and go to pour your instant coffee in it. As soon as that touches, the whole thing boils and blows up in your face. That's a superheated liquid. It's heated above the point that it should boil. Okay? And that actually does happen. You can probably go on YouTube and find it. Okay? I would suggest not doing it though. Because imagine having water supposed to boil at 212 Fahrenheit. If it's heated above that, do you want that blowing up on you? No, you don't. Okay? Leave it to the fools on YouTube. Right? This is another solubility curve. Some salts, including sodium chloride, actually don't change solubility with temperature. Sugar does though. Okay? Just skip a whole bunch.
It jumped back.
Jump back.
Jump back?
I have a solubility curve before the temperature, and we did temperature.
Is it this?
Oh, yeah, there it
Is
is.
Yeah.
Before gas pressure.
Maybe I opened the wrong file. We'll figure it out.
Oh, it's all here. It's just-
Yeah, it's all
Well,
there.
I cut out a bunch. So I started with last year's lecture and cut out a bunch. Maybe I opened the wrong one when we started. But with sugar, as you heat, solubility goes up. At 0 degrees Celsius, you can dissolve 175 grams of sugar in 100 milliliters of water. If you heat it to 100 Celsius, now you can put 475 grams of sugar in that same amount of water. That's a very large change. It's a problem. It says sodium chloride has a solubility of 38 grams per 100 grams of water at 25 degrees Celsius. That means at 25 degrees Celsius, you can dissolve 38 grams of salt in 100 grams of water. If we take 45 grams of sodium chloride and add it to 150 grams of water, what kind of solution do we have? Supersaturated, saturated, or unsaturated?
Saturated.
Okay, saturated, I hear unsaturated. Anybody want to say supersaturated? No supersaturated. Does anyone want to defend what that says? Go ahead.
Well, since the temperature is actually sort of irrelevant,
Right,
so we're just going to ignore that number.
right?
So we're just going to take the ratio of 38 grams over 100 grams to 45 over 150, which I think understanding is 0.03. So it's
Okay.
going to be a smaller ratio that we can actually put in more salt to the 150 grams of water.
Right. Okay. So what he did is he took the ratio of the grams of the salt to the grams of water. So he said the solubility is 38 grams of NaCl per 100 grams of water. If you do that division, you get 0.38. Okay? Then he took the ratio for the other one. He said 45 grams of NaCl divided by 150 grams of water, and you got what? 0.30. So this one, there's less salt per water than in this one. And if this one is saturated, there's less salt in that one. So this is unsaturated. Okay? That's one way of doing it. So anyone? I'm sorry?
Don't just make sure the one that has the less.
Yes. So by definition, this one tells us this one is saturated.
So when you get that number for solubility of a compound, that's going to be the maximum, right before.
That's the dividing line between supersaturated and unsaturated.
Okay, so anything that's not that number, like below it, would be described as unsaturated.
Right.
You know, it still has some, but it's not, the word described as unsaturated.
Correct. When I look at this, I do the math in my head a little differently. This is completely correct. Okay? But it's important to find what makes sense in your head. Does anyone else see this different?
I just multiplied it by 1.5.
That's how my mind works here. I say this tells me in 100 grams of water I can dissolve 38 grams. Here I have 150 grams of water, which is 1.5 times as much, which means I can dissolve 1.5 times as much salt. So I would take 38 grams of salt times 1.5 equals what? 57 grams of salt. That means in 150 grams of water, I can dissolve 50 grams of salt, but I only have 45, which is less than this. So I'm not saturated, so it's unsaturated. Okay? They both got the same exact answer. They're both equally correct. This is a good place to stop. Let's take a break. You will start at 7:37 on this clock. Somebody remind me to.
Or was probably
So-
just talking about.
We said we were going to start talking about solutions in terms of numbers. There are a lot of different units that we can use to express the number for our solution. Luckily, one of them is by far the most common. Okay? We can talk about percent by mass. This is very similar to something we've done before. Say we have 50 grams of salt in 100 grams of water. How do you think you would find the percent by mass of the salt? Ratio. So you would take the mass of the salt divided by the total mass. So it'd be 50 divided by 150, which is what? 1/3, so 33.33%. percent by volume, if you have 50 liters of sodium chloride and 100 liters of water, it would be 33.33% sodium chloride by volume. You can also do a weird mass volume thing. Unfortunately, this is what most scientists use, even though it's not correct. You can do parts per million, parts per billion. This is essentially percent by mass, except when you solve for a percent, you know how you multiply by 100 at the end? For parts per million, you multiply by a million instead of 100. Parts per billion, you multiply it by a billion rather than 100. Then there's molarity. Molarity is the one we're going to spend all our time on. Molarity is a capital M. This is what was on all those labels in the lab. It's a number with a capital M. That's saying it's 0.1 molarity solution, and we say that as a 0.1 molar solution. And there's also molality, one letter difference. Same letter unit, but lowercase. Don't get them mixed up. Okay, we'll talk about both of them, but they are different. Molarity is a common one. Molality is very uncommon. So like we said, for percent by mass of a solute, just take the mass of your solute, divide by the total mass of the solution times 100. That's it. You're done. So here's an example.
Wait, can you go back?
Yeah, if you go back, it kind of lightened it up.
Yeah.
I deal with mass of solution, not mass of.
Solvent?
Yeah.
Yes, it is mass of solution, not mass of solvent. It's the total mass of the solvent and the solute combined. Got a copy? Here's an example where you would use that. What is the percent by mass of acetic acid in vinegar that contains 2.70 grams of acetic acid and 122.8 grams of water? Simple math, right? How do I do that? What's the equation? Mass of solute divided by mass of solution. What is the mass of my solute?
2.70 grams.
2.70 grams. What is the mass of my solution?
128.8, or speaking out, 122.8 grams.
Wouldn't you add the two?
You would add the two.
Ah, yeah.
It's mass of the solution. So it's 2.70 plus 122.8 equals 2.70 over 125.5 equals what? Don't get times 100.
2%.
2.15%. 3 sig figs? 3 sig figs. Here's another one. Put a percent by mass percent of sodium chloride in a solution where you add 10 grams of sodium chloride to 50 grams of water. What goes on top of my fraction? 10.0 grams. What goes on the bottom? 60.0 grams equals 0.167, then times 100 equals 16.7%. Percent by volume is the same exact math, you're just dealing with volumes instead of masses. So we're taking 205 milliliters of ethanol and enough water, it doesn't say how much, but it says enough water to give us 235 milliliters of solution. What number is going to go on top of my fraction? 205. What number is going to go on the bottom of my fraction? 235. So you have 205 divided by 235 equals 0.872, which equals 87.2%. That easy. Cross this one out. I'm not going to do this one. Okay? If you can find it, I guess. Mass volume. Now we come to the biggie. Molarity. Molarity, the capital M, is moles of solute divided by liters of solution. Is that on here? That is not on here. You will definitely need to have that memorized. Here's an example, calculating molarity. We have a solution that has 117 grams of potassium hydroxide dissolved in enough water to give us a total volume of 2.00 liters. This is telling us that the molar mass of potassium hydroxide is 56.11, so we don't have to calculate it ourselves. What is the molarity of the aqueous potassium hydroxide solution? What is the equation for molarity?
Moles of solute.
Molarity equals moles divided by volume. Okay. Do we have either of those? Yes. Which one? Volume. Total volume 2.00 liters. That one we can just plug in. So we have moles divided by 2.00 liters. Do we have moles? No. Not directly. Do we have moles indirectly?
Yes.
Yes. How?
Yeah.
Grams.
You have grams. Convert from grams to moles. So let's do that over here. We have 117 grams of KOH, and it tells us that 56.11 grams KOH equals 1 mole KOH. And so what does that come out to be?
2.005.
2.085? 0.085 moles KOH. So now we can take that number, plug it in here, equals 2.085 0.5 divided by 2.00 equals 1.0425 molar 366. 1.04 molar KOH. Yeah.
Is aqueous required on that or no?
No. No. Okay. In a lab, this is the kind of calculation you do over and over and over again. Okay? Because every solution you do, every solution you make is in molarity. So to make it, you have to do this calculation. Okay? If we have a solution and we heat it up, the volume of liquids changes slightly with temperature. So if I have a sodium chloride solution and I heat it up, if we look at our equation for molarity, moles over volume, and I heat it up, is my number of moles going to change? No. But my volume changes. Slightly, but it does. Which direction is the volume going to go? Up. So what does that do to my molarity? It makes my molarity smaller. So that is a weakness of molarity. It is temperature dependent. In most cases, those volume changes are insignificantly small. But it is an inherent weakness, so they come up with molality, which is completely temperature independent. Molality with an L is moles of solute divided by kilograms of solution. Okay? Thinking about working in a lab, why would this be inconvenient? Kilograms is a lot. Say you know you wanted X amount of sodium chloride, and you know the concentration of your sodium chloride solution. You know, okay, I need to add this much volume of it to it. Okay? What's easier? To measure out 20 milliliters of a solution, or to measure out 0.02 kilograms of a solution? Or it's even say 20 grams of a solution. Which one's easier? Milliliters. Okay? You pour it into your graduated cylinder, it's above the line, you pour a little bit out. It's below the line, you pour a little more in. If you are doing it by mass, you end up at the scale with a little dropper going drip, 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 drip. And while you're doing that, it's going to take so long, your solution is going to evaporate, and your mass is going to change, your molality is going to change. Okay? So this is not convenient, but in certain situations, you have to use it. So here's another example. I'm going to calculate the molality. Okay? So again, we have potassium hydroxide. We have 56.7 grams potassium hydroxide, and we're going to dissolve it in enough water to give us 245.8 grams of solution. What is the equation for molality?
Molality equals moles of solute over kilograms of solution.
Right. Molality, lowercase m, goes moles of solute over kilograms of solution. Do we have either of those?
Yes.
Which one?
We have,
grams, but we have to
oh,
go
mass.
We have grams, which we can easily go from grams to kilograms. You can do it dimensional analysis. Can anyone do that in their head at this point? Do the decimal. How many places? 3. So which puts you where? 0.2458 kilograms. Yep. So our kilograms of solution is 0.2458 kilograms. Now we just need moles of our potassium hydroxide again. So
6.7 divided by
56.7 divided by what?
56.1.
56.11. 56.11 equals 1.01
Mole, QH.
moles. Okay. Is everyone comfortable going from the grams of KOH to moles of KOH? We have that number plus 1.01 moles. 1.01 divided by 0.2458 is 4.11. 4.11 molal KOH. Capital M is a molar solution, lowercase m is a molal solution. It's just a whole lot harder to say, too. Next type of calculation is dilution calculations. For dilution calculation, we're going to have M1 V1 equals M2 V2. Just like before, the 1s are before, the 2s are after. V's are still volume, M's are molarity. Okay? It's going to work, if you, it would actually work with other types of concentrations also, like percent and things like that. But generally, you're going to do the problems with molarity. So, just like you would expect, there are 4 variables. What's a problem involving this going to look like? They're going to give you 3 of them, solve for the 4th one. Okay? Don't worry too much about that. Here it is rearranged for you, if you want, if it's helpful. But be sure you can rearrange that. And that equation is not on here. M1 V1 equals M2 V2. Not on here. Make sure you memorize that. So here's the problem. We have 175 milliliters of a 1.6 molar solution of lithium chloride. We dilute that to 1 liter. Determine the new concentration. So we have M1 V1 equals M2 V2. Which 3 do we have? Which one do we not have? We don't have M2. So we're trying to solve for M2, which means M1, V1, V2 have to be given to us. What is M1? 1.6 molar. What is V1?
175 milliliters.
175 milliliters. What is V2?
1 liter.
1.0 liters. Do we have to change anything?
Yes, we have to change it to milliliters or liters.
Correct. We either have to change the milliliters into liters, or we have to change the liters into milliliters. Doesn't matter which one, but they have to be the same unit. Which one do you want?
V1 to the 0.175 liter.
So David is saying that 175 milliliters is 0.175 liters. Now they're both in liters. We can just plug them in. So M1 is 1.6 times V1, 0.175 equals M2 times 1.0. M2 equals 0.128.
128.
0.28 molar lithium chloride. Not hard, right? Just like the gas laws, find the one variable you don't have, plug in all the other ones after you change the stupid units, and solve, do the easy algebra. Here's another way of looking at dilution problems. You need to make 10 liters of a 1.2 molar potassium nitrate solution. You're doing an experiment, you know this is what you need. For one reason or another, you can only use 2.5 liters of what we call your stock solution. Your concentrated solution that you use to make all of the solutions that you actually use. Okay? You can only use 2.5 liters of your stock solution. The question is, what molarity does this stock solution have to be for that to work? So it's still M1, V1 equals M2, V2. Which one are we solving for now?
M1.
M1, yes. We know what we're trying to dilute to is 10 liters, that's the V2. That is our M2. That's our V1. The only thing that's missing is M1. So in this case, we're looking for M1. So what is V1?
2.5 liters.
2.5 liters. What is M2? 1.2 molar. And what is V2?
10 liters.
10.0 liters. Plug them in. M1 times 2.5 equals 1.2 times 10.0. M1 equals what? Four point 4.8 molar KNO. Okay. Same problem, same equation, just we're solving for M1 instead of M2. So you can do the reverse dilution in your head, which is generally what you end up doing in the lab, because you say, you write out your experiment, you say, I need this much of this concentration of solution. What's on the shelf here is this strength, this concentration. How much of it do I need to dilute to make the solution that I want? That's the calculation you do a lot. And a third way of looking at it is how many just like what I mentioned, you have a 5 molar copper 2 sulfate solution. How many milliliters? 5 milliliters. Cross that one out. That one's going to lead you down a very dark, long, angry, frustrated path. Okay?
Do you have a final?
No.
Okay.
No. When I went through these slides, I did the first example in my head, and then look at that last one, and now I remember it from last year. It's not a happy memory.
We'll grab that whole stress.
Okay. Here's the third one. You need 100 milliliters of 3 molar hydrochloric acid solution. What you have in your stock solution is 13 milliliters of 10 molar hydrochloric acid. And the question is, can you do your experiment? How would you figure that out? You have M1, B1, M2, B2. So what do?
Plug them in and see if they're equal.
You could do that, yes. If you plug them in, what is M1? 10. I would say M1 is this, the 10 molar. So you have 10. What is V1?
13.
13 milliliters. Set it equal to, that's M2, 3 molar times 100 milliliters. So that's 300, and that is
130.
130. So they're not equal. But you're going to have to really stop and think about, what does that mean? Does that mean does that mean you have more, or does that mean you have less?
More concentrated solution.
Concentration of the solution we have is greater than.
There are, in order to figure out which one's more, you have to go back to a molarity equation. Mole divided by volume. If I take molarity times volume, I get moles. So that's what we did here, right? Molarity times volume. So what this number is moles. It's not, it's millimoles because it's milliliters and not liters. But what this is telling us is how much of the HCl is in each side. So we need 300 of HCl here, but we only have 130. So we cannot do it. Okay? Does anyone see another way you would go about this?
Adding more hydrochloric acid to it.
Mathematically, to do this problem.
I was thinking a ratio. I just like those.
You can take a ratio. What I would suggest, how I would do it, and they're all perfectly equal answers, they're going to come out the same way, is I would say I need 100 times 3. I know my stock is 10 molar. What of the solution do I need? Solve for V1. That's, if I find out I need 20 milliliters, I only have 13. If I find out I need 10 milliliters, I have 13, I have enough. Okay. To me, that's the most straightforward way. Whichever way works for you, do it. They'll all get you to the same place. What's on the next slide after this one?
On ours or on yours?
On yours. Well, it's precipitation reactions?
Lines for
Lines
reaction.
for reactions that
Quantities
occur
for
in the
reactions.
solution. And then precipitation.
this is our last slide, 'cause I know those should have been, the quantities of precipitation reaction should have been deleted. So with dilutions, in the lab, we talk about them, we have kind of slang terms to talk about dilution. It's called dilution factor. That tells us how much it's diluted. We can say something is a twofold dilution. That means the volume is now twice as large, which means our concentration is half as high. We can also say it's a 2x dilution, which means the volume is now twice as much, the concentration is half as much. It's basically just telling us the ratio between the old volume and the new volume, okay? So you may see either of those anywhere, okay? If you dilute 10 mils to 100 mils, how would you say that? It's 10 times dilution, that's a 10x dilution, that's a 10-fold dilution. It's all the same thing. Okay. So we will stop here, and we'll